Hello. In this lecture, we talk about parity and parity violation. So we talk about a discrete symmetry. A little bit of history in particle physics. Lee and Young in the 1950s wondered if there's any experiment testing parity invariance. There were many tests which had to do with a strong interaction and electromagnetic interaction, but as it turned out, parity invariance had never been tested in weak interaction. And so Lee and Young were motivated in this because there was a puzzle at the time, so-called tau theta puzzle, which turned out to be kaon decays into various particles. And in that puzzle, they saw decays with the same lifetime, but different spin states. And so they couldn't quite understand this, and were trying to understand whether or not one can have an experiment to test this. So the experiment they proposed is one where you look at a nuclei and observe beta decay. So there's an electron coming out of the beta decay. If you're able to align the spin of the nuclei and put this in front of a mirror, you see that the physics going to the mirror state is not conserving parity. You see that in the mirror, the spin in the opposite direction, but the momentum of the electrons still come out in the bottom. So there's clearly some change in the physics going on in the mirror state. So Madame Wu actually took up this idea and immediately tested this in the same year. She was a Chinese-American physicist born in China and then studied in Berkeley together with famous people there. Lawrence is one of them. After the war, or in the war, she joined the Manhattan Project and made very, very important contribution to the Manhattan Project based on her thesis work. As a fun fact, she was married to another Chinese American, the grandson of the first president of the Republic of China. As I said, in 1956, she conducted the Wu experiment, and in the following year received the Nobel Prize in Physics for the finding. So really briefly, we're going to have another discussion of the Wu experiment later on. What she did here is she studied cobalt-60 decay into nickel beta decays. And what she was able to do experimentally with a magnetic field, align the cobalt-60, and then just count the number of electrons coming out. And it turns out that the number of electrons coming out on the bottom and the top are not the same. She did this by reverting a magnetic field, and the experimental data is shown here. You see as a function of time, so you just look at counting rates as a function of time after injecting the probe, and you do the measurement by reverting the magnetic field. And you see very clearly here that there's an asymmetry in the beta decays, and that asymmetry immediately tells you that there has to be parity violation in beta decays or in weak interaction. So she found that this specific picture here violates parity, and this is a dramatic signature of the weak interaction, and we'll later see how we can actually understand this. Note that parity is conserved in electromagnetic interaction and strong interaction. One more word on parity inversion. You can define a parity operator, and if you apply this parity operator, for example, on a vector with x, y, and z components, you simply turn the direction over here with a minus sign.